Not literally. It's one different. So there's another that was used as a failsafe, although I would suggest maybe, Lori, that we go ahead and put that in the archive so there isn't any confusion.
Yep.
And I can share a link that we're starting now. Are we recording, by the way?
Philip, can you confirm that you're recording?
Not now, but I will start when just in start.
Yeah. Why don't we go ahead and hit record, because I'll send out a message and we'll have people jump in right now.
Okay, sure, I will start recording.
Looks like we lost you on stage, Justin, so you'll want to jump back on. There it is.
Okay, can you hear me again? Sorry, I tried joining from my laptop and I guess it kicked me off my iPad. So let me just kill my laptop. Okay, should I share my screen and we can get going?
Yeah.
Sounds great.
All right, and and so if anyone wants to ask questions, exactly what is the procedure now that we're trying stages?
Good
Yeah.
question. We haven't
So-
really fully specified it. I think my preference would be that people ask their question in chat, at least, and I think that helps so that they have to kind of formulate their questions so that they're not fumbling through asking the question live. So they ask it in chat. I will basically say, hey, someone has a question. I'll pop them on stage. They'll ask their question to you.
Okay, sounds great. And yeah, I won't be since the laptop thing was a fail. At least today, I won't be seeing the chat. So yeah, you'll
Sounds
have to
good. I will be responsible for tracking the chat.
Okay, great. Well, thanks for setting this up. This seems like a great setup. So I'm excited to try it. And today we're going to be talking about multilinear, polynomials and what are called low degree extensions and multilinear Lagrange interpolation. So I think 2 sessions ago we saw univariate Lagrange interpolation. So that's Lagrange interpolation for univariate polynomials, but now we'll be shifting to these multilinear ones. They take a little bit of getting used to, but actually once you get used to them, I find they're often simpler in many regards than the univariate polynomials. But most people are familiar with from high school math or something. And these multivariate ones and multilinear ones in particular are exactly what you want for if you're designing interactive proofs, which in my view are sort of lead to the fastest prover snarks as well. And one of my goals sort of in life and in this study group in particular is to try to convey why these multivariate techniques are so powerful and key to performance. And the reasons are a little bit subtle. So I'm still always looking for better ways to try to convey them. All right, so let us introduce multilinear extensions. And I guess before that, I'll just remind you what is a multilinear polynomial. So a multilinear polynomial, let's say in n variables, let's call it P. It's just a polynomial where the degree in each variable is at most 1. So let's see, as an example, if P is like x1 times x2 plus 3x3 plus, I don't know, x1 times x3, here n is 3 variables, this would be multilinear, right? Because you just never see an exponent that's bigger than 1. If I were to make one of the exponents say 2, now it wouldn't be multilinear, and similarly, if I were to make it 5, that's also not multilinear. So multilinear means degree in each variable is at most 1. So you can have terms that like multiply all the variables together as long as each individual variable has, an exponent of 1 or 0. Okay, is, 1 or 0. Okay. And what I want to say next, so let's talk about multilinear extensions. So suppose we have a function f. F is not a polynomial. F is just a function. So its domain is 0, 1 to the n. And its range, its outputs live in some field. Okay. Something to mention is that like any field has 0 or 1 as entries. Are elements of any field. Right. So you can view 0, 1 to the n as like a very small subset of the field, to the n. Literally every field by definition has to have 0 in it and 1 in it. Beyond that, different fields differ. Yeah, so pictorially, you can think of f just by listing all of its evaluations. So here, if n is 2, we might depict f as follows. So it has 4 inputs. 0, 0, 0, 1, 1, 0, and 1, 1. And so let's say like f of 0, 0 is, I don't know, 3. F of 0, 1 is 5. F of 1, 0 is 4. And f of 1, 1 is, I don't know, let's say 8. Okay. So f is just a function, with who's mapping bit strings to field elements. That's it. And here's a simple fact. This fact is proved in the book, but I think I'm not going to cover the proof. Just take it for granted. So for any function f whose domain is 0, 1 to the n, and whose range is some finite field, there is a unique multilinear polynomial. So I'm going to say this verbally and then write out something a little more formal. The polynomial I'm going to call f twiddle, and the polynomial agrees with f wherever f is defined. Okay, so that is if you feed into f twiddle an input in 0, 1 to the n, you get out whatever f spits out. So f twiddle of x equals f of x for all x in 0, 1 to the n. Okay, now this is called a multilinear extension. F twiddle is called the multilinear extension of f, or MLE for short, multilinear extension. And it's called an extension because whereas the domain of f is 0, 1 to the n, f twiddle, since it's a polynomial defined over the field, you can evaluate f twiddle, outside of 0, 1. Right. So pictorially, if I move this picture of this, particular f down to get more space, so f itself only has 4 evaluations, but f twiddle, has domain size, field to the n, which in this case, when n is 2, that's field size squared for n equals 2. So think of a field that has size about 2 to the 128 or something. F has only 4 inputs, but f twiddle has 2 to the 256 inputs, right? So if you're going to draw f twiddle, like write down its entire list of evaluations, it's a vastly bigger square hypercube of evaluations than f itself. You're moving from 0, 1 to the n to field to the n, and the top left corner, the top of the evaluations of F twiddle is exactly the evaluations of F. So that's why we call it an extension. It's sort of, just like taking F and, replacing it with a much bigger object of which, sort of a redundant encoding of F. You're like taking F, but then adding all sorts of other stuff on top of it. And because F twiddle is multilinear, it actually means if you sort of look along any row or column here, what you get is a line. Yeah, so that's like saying, if I look at, this particular multilinear polynomial here, if I were to fix like x2 and x3 to fix values and leave x1 as a variable, you get out something degree 1. And so that's a line, right? So if I like fix x2 to, I don't know, 6 and x3 to 7, I get out some line, some degree 1 function in x1. That's a line, which means it's pretty easy to like look at, F and write out the evaluations of F twiddle, right? So like as I go along this top row, moving from, input 0 to 1 moves me from 3 to 5, so that's like the line that maps 0 to 3 and 1 to 5. And so what does that line map 2 do? It maps it to 7. What does that line map 3 to? It maps it to 9. It maps 4 to 11 and so forth. Similarly, going along this row, 0 maps to 4, 1 maps to 8, 2 would map to 12, and 3 to 16, and then 20. As you go along a column, it's the same thing. So 3, 4, 5, 6, 7, 5, 8, that's difference is 3. So 11, 14, 17. So you just sort of get used to this stuff, right? And then, if you go along, this row here, 5 and then 11, next would be 17, 23 and so forth, 6, 14, next would be, hopefully I'm doing all the math right, 22, 30. Yeah, so every row and column is just a line. Okay, so that's multilinear extensions. Yeah, let me pause and see if anyone has any questions about the multilinear extension. Okay, so this is like a multilinear analog of the fact that, if I give you, if I'm talking about univariate polynomials, and I give you sort of, if we're talking about degree n univariate polynomials, and I give you like what would be n plus 1 points, x1 to go out of, let's say 0 maps to some value y0, 1 maps to y1, and n maps to yn. In univariate land, there exists a unique degree n polynomial with that behavior, such that f of I equals yi for I equals 0 to n. And so this is just the multilinear analog of that. There is this like funny thing where in univariate land, like any set of n plus 1 points uniquely defines the univariate polynomial of degree n with that input-output behavior. So any set of n plus 1 points is what's called an interpolating set for degree n univariate polynomials. In multilinear land, the interpolating set has to be a product set. So, there's nothing super special about 0, 1 to the n. Like you could do like a comma b to the n, for any, distinct a and b, so you could do like minus 1, 1 to the n instead of 0, 1. You could do, it doesn't matter, like 7, 8 to the n if you really, wanted to. But in interactive proof land, like 0, 1 to the n tends to be like the right thing to do. And this will become clear over time. I 1, 1 to the n. I prefer 0, 1 to the n. Anyway, I'll just leave it at that right now. So that's multilinear extensions. Okay, I'll pause again. Any questions? All right. So just to be clear, like any f whose domain is 0, 1 to the n, actually it has many extension polynomials, but only exactly one of them is multilinear. So for example, let's again consider, I don't know, a 3-variate function now, and think about its multilinear extension. Okay, now imagine I take the multilinear extension and I add to it like x1 times 1 minus x1. Okay, now this is 0 for all, x1 in 0, 1, which means, by adding this term to f twiddle, I did not, alter f twiddle's outputs on 0, 1 to the n, right? So if I call this, I don't know, f hat of x1, x2, x3, so that is f hat of x equals f twiddle of x equals f of x if x is in 0, 1 to the n. Okay, but if I were to evaluate f hat and f twiddle outside of 0, 1 to the n, they would not be the same. So f hat of x does not equal f twiddle of x, for almost, for almost all x, in the whole field. So what's happening is if I were to write the evaluation table of f hat rather than f twiddle in this picture, the top left square wouldn't change at all. It would be the same. This is 2-variate, but whatever. The top left square stays the same, but everything in blue might change. And so, f hat we would still call, a low degree extension. As we've discussed before, the term low degree is a little bit vague, but certainly, degree at most 2 in each variable would qualify as low degree. So f hat is a low degree extension of f, but it's not multilinear, right? And there's only ever one. There's the multilinear extension is always unique. There's exactly one. Okay, yeah. So sometimes we'll see all, regularly, quite regularly actually, we'll sometimes need to use non-multilinear extensions, basically because like the snark verifier will be able to evaluate the non-multilinear extension super duper quickly. It's like we'd always like to use multilinear extensions, just sometimes we can't because they're not quickly evaluable by a snark verifier. And we wind up using the sum check protocol often to kind of move between a non-multilinear extension and multilinear ones. And this, don't worry about what that means right now. That'll become clear in the next couple weeks. Okay, so that's low degree and multilinear extensions of functions whose domain is 0, 1 to the n. And so now we need to talk about multilinear Lagrange interpolation. Okay, and here the problem is the following. Let's say the input, we want to give an efficient algorithm for something. So what is that algorithm trying to solve? Let's say the input to the algorithm is the list of all 2 to the n evaluations of some function f whose domain is 0, 1 to the n. So that is,
Before we go on, there are a couple
Yeah.
of questions. Can we pause and take
yes,
a look at them?
please, let's do it.
The first one is from Nakul and says, what would an example be arithmetization? And admittedly, I'm not sure what he means by that. So I'm going to invite him up if he wants
Great.
to hop in. Cool. Nakula, you should be able to speak now.
Yeah, I was talking about when you mentioned that sometimes we might want a low degree extension that's not multilinear. So I'm wondering if an example here would be when we use the arithmetization of the circuit.
Yeah, that's a great question. And so let me give an answer to this. I'll write in red for a minute. So there's an exercise in the book about this, but I'll just give away the solution. So arithmetization is a slightly vague term. It's generally a way to turn computation, things like circuits, which don't necessarily have anything to do with polynomials, into statements about polynomials. Yeah, so let's, how do I want to say this? Yeah, let's talk about a Boolean circuit real fast, or a Boolean formula. So let's say, so this is end. This denotes the end function. And let's say, I want to keep this not too long. Let's say this one's OR. And then we'll have one more end gate. Okay, so this is a Boolean formula, or Boolean circuit, I guess. And a very common question in computers, or problem in computer science, is to try to figure out, is there any assignment, true false assignment to these three variables that causes the formula to output true. And arithmetization is a technique to turn this Boolean circuit, where the operations are ands and ors and nots, into what you could call an equivalent arithmetic circuit. So this is one meaning of the term arithmetization. Again, people use it to mean lots of kind of loosely related things. So an arithmetic circuit has inputs that are elements of a finite field, and the gates don't compute ends and ors and nots. They compute like addition, multiplication over the field. And so without going into too much detail, it turns out you can, here's an arithmetic circuit that is equivalent to this Boolean one. So ends turn into multiplication, right? And what's going on there is, we represent, false with 0, and true with 1. And, end is saying, are both of my inputs true? Same as saying, are both of my inputs 1? And so, if I multiply two numbers together and they're both either 0 or 1, then the product is 1 if and only if they're both 1. So that's like an end. So n turns into multiplication, and or turns into some more annoying thing, where, so like or of x2 x3 is actually the multilinear extension of that function is x2 plus x3 minus x2 times x3. And this is something you can just check, that this polynomial maps 0 0 to 0, 0 1 to 1, 1 0 also goes to 1, and 1 1 goes to 1. So this little expression does the same thing that OR does if you feed it Boolean inputs. So we would add x2 and x3. Sorry, x2, and we would then also multiply them together and then subtract the results from each other. And then finally, this end gate at the end is multiplication. Okay, so I went through, a big song and dance, and what I got was an arithmetic circuit that, if you feed it an input in 0 1 to the 3, spits out the same value that the Boolean circuit does. Okay, so this circuit, this arithmetic circuit, actually describes a univariate polynomial of what is its degree? Maybe this has degree 2, and this has degree. Sorry, it's a multivariate. It's a three-variate polynomial. I guess it has degree in each variable. I think. I don't feel like writing this out. It's x1 times x2 that captures this gate, times the difference of x. Yeah, I guess it's just what I wrote before. X2 plus x3 minus x2 times x3. Okay, so this is G. So this arithmetic circuit computes some polynomial g in the three variables. Okay, so g is an extension of the function computed by the circuit. Yeah, that right. So like if I feed this polynomial any input in 0, 1 to the 3, it spits out the same thing that the circuit does on that input. Okay. But this polynomial, that the circuit computes is not multilinear. Because here we have an x2 getting multiplied by an x2, for example, and that's going to result in some degree 2 term, degree 2 and x2, that I expect is not canceled out. I'd have to write it all out in like the appropriate basis to be 100% sure it's not multilinear, but I in general it won't be multilinear. This polynomial g, the verifier can evaluate efficiently at a single point, just by going, gate by gate through the circuit, right? So if I want to know like g of, R1, R2, R3, well, all I do is, this gate winds up computing R1 times R2. This gate computes R2 plus R3. This gate computes R2 times R3. This gate subtracts their 2, and then we product those together, and you get out g of R1, R2, R3. So just by going gate by gate through the circuit, you can evaluate g at the desired point. Okay, great. And so that's a way to get a non-multilinear extension of a function that can be efficiently evaluated. However many gates there are in the circuit you started with is roughly how long it takes to evaluate the arithmetic circuit. Okay, now it turns out like suppose the verifier could evaluate the multilinear extension f twiddle of f. Here, remember this f is the function computed by the circuit, right? I claim that that's enough to ascertain whether or not the circuit is satisfiable. Okay, which we think this is an NP-hard problem. So what I'm saying is evaluating multilinear extensions really, really quickly is powerful enough is as hard as solving circuit SAT. Okay, and why is this? So if the circuit is not satisfiable, so if the circuit is unsatisfiable, so that is it maps all inputs x in 0, 1 to the n, in my example, n is 3, to 0, then, my claim is then f twiddle is the identically 0 polynomial. Okay. And this holds, just because multilinear extensions are unique, right? So if f maps everything in its domain 0, 1 to the n to 0, well, that is the same as what the all zeros polynomial does on that domain. The all zeros polynomial is obviously multilinear. It has degree 0 in each variable. Since multilinear extensions are unique, 0 must be the multilinear extension of f. Okay, which means to check if the circuit is satisfiable or not, I would just pick an R, at random from field to the n, and see if f twiddle of R is 0. and so if f is unsatisfiable, then indeed f twiddle of r will equal 0, because it'll be the f twiddle will be the all zeros polynomial. And if f is satisfiable, if the circuit is satisfiable, then f twiddle will not be the all zeros polynomial. And that means with overwhelming probability, if you evaluate it at a random point, it won't spit out 0, just by the short zip lemma or something. So that was a very, very long way of saying arithmetization is exactly the kind of example where you might wind up with a non-multilinear extension. And in fact, if the multilinear extension in this setting were efficiently evaluable, you'd actually be able to solve an NP-hard problem, efficiently, which we believe is impossible. So, that's very, very strong evidence that if you want an extension of this particular function that is efficiently evaluable, you cannot use the multilinear one. You have to go to a higher degree one. Okay, so that was more of an answer than probably anyone expected, but you're slowly getting used to that. So follow-up questions about that explanation.
Yeah, just one follow-up. Thanks for the explanation. One follow-up is, so I guess here there was this trade-off um between, okay, so even, although it's not multilinear, I guess there's some kind of a bound on the degree of the polynomial that we'll have, and we were okay with it being slightly more than one because we could compute it quicker. So is there always going to be this trade-off between how fast we can evaluate it and how big the degree is going to be?
Yeah, there often is a trade-off, but I don't know. Typically, like as soon as you go to degree 2 in each variable, you can okay, it's application dependent, but in most snarks, as soon as you allow degree 2 in each variable, you often get something that is efficiently evaluable. And that's actually why most applications of the sum check protocol, like the polynomial that's being summed, has degree at most 2 or 3 in each variable. It's like degree 1 in each variable, that is a very special thing. And as this example shows, that somehow like evaluating multilinear things is just a very powerful power. Gives you a lot of power. As soon as you allow degree 2 in each variable, suddenly a lot of that power kind of goes away. And yeah, I basically think in practical applications, there's rarely a reason to go beyond degree maybe 3 or 4 at the very highest in each variable, and often degree 2 is fine. There's probably
Thank you.
Yeah, sure. Yeah, I'll stop. Right. Yeah, I could say more, but I'll stop there. Yeah, there is so the degree of this G can be as much as sort of the size of the circuit you started with, if you define size, carefully. And so whether or not that constitutes, quote, low degree is a little bit application dependent. Certainly in any interactive proof or snark that were to use this G, we would need the field size to be at least the degree of G minimum. And so, if you started with a really big circuit, you might not actually consider the degree of this thing to be, like low degree. Again, low degree is sort of a vague term. And whether something sort of really should be considered low degree or not depends on setting or application or whatever. So this particular arithmetization approach doesn't get used directly in practical snark design, again, because if this circuit is big, this thing does not have degree like 2 in each variable. So what we would actually do in practical snark design is something like take this circuit and not use this G itself, but like kind of break the circuit into pieces, and the pieces are so simple that we can actually identify a degree 2 extension that we can use in each part of the protocol. But now the fact that we kind of broke the whole circuit into pieces means you know, we need to kind of handle each piece one at a time. So anyway, I'm going to stop rambling here. Hopefully this is giving some flavor of what comes up in practical snarks. Basically, this technique of just taking this G and like using this in a proof system and that's it. This is what people did in the early 1990s with like the IP equals P space result that kind of set off the whole area of verifiable computing. And then the modern techniques, you know, sort of recognize that this particular G actually has overly large degree. If you actually want, you know, a prover you can run in the real world, and so we start doing more clever things to get lower degree Gs. But again, you're never gonna get G to be multilinear because if the verifier could kind of evaluate that multilinear thing directly, it could solve an NP hard problem. Okay. More questions? Was there a second question in the chat?
Yes, I just invited him up to ask it.
Okay.
I don't know why he's not speaking. I think the gist of his question was that, right, if we have a non-multi. Okay, go ahead.
My mic was off, so maybe I will ask the question. So, as you defined it before, we have a function over the Boolean cube, so we get a multilinear extension. So my question is, because we get a multilinear extension, it means that polynomial of degree at most one in each variable. So my question was about if we start from, let's say, a general polynomial, not particularly multilinear, we can get the function, but at this point over f to the n. So can we get the multilinear extension of a general polynomial? We have for example, polynomial at most degree 3 or 4, I don't know, in each variable, we get the function over the f over to the n. It's not the Boolean, but let's say we take b equal to the field, and we try to construct a multilinear polynomial extension for this polynomial.
I think the short answer is that like you.
There is a problem with the cost.
I think the short answer is that like you can take like once you have your polynomial defined, you know the values on the 0, 1 to the n, you get a single multilinear polynomial out of that. However, there are lots of polynomials that meet that same like set of points. There's only a single multilinear one of them. So you could start out with your degree 10 polynomial, but once you restrict it to those points and you extrapolate to the multilinear, you get a single multilinear.
Yeah, and another way of saying that is like if you give me a function that's defined over the whole field, like in general, that function might be a very, very high degree polynomial. And you know, any multilinear polynomial might differ at a lot of points from that function, right? You only get you're only guaranteed to get agreement with some multilinear polynomial if you only pay attention to 0, 1 to the n. Yeah, and sort of a related point is, you know, let's say I care about like 0, 1, 2 to the n rather than 0, 1 to the n. Then you can, this is still an interpolating set, but no longer for multilinear things. So there is a unique polynomial of degree at most 2 in each variable. You know, such that, you know, so let's say this is the domain of F, such that, let's call that, I don't know, P, such that P of X equals F of X for all x in this domain. Right. So in general, there's really like a spectrum between univariate and multilinear. And univariate is like, multilinear, it's like doing this general thing where like n equals 1, and so the size of the interpolating set is 0, is like n plus 1. So if n equals 1, we have univariate interpolation. But in general, like, if you have like 0, 1 up to k, to the t, right, then you're talking about t-variate polynomials. It's an interpolating set of t-variate polynomials, degree at most k in each variable. K plus 1, maybe, k. Yeah. And similarly, like in SNARK design, you can often get certain trade-offs. There's like a spectrum of trade-offs between like, number of rounds of the protocol before you apply Fiat-Shamir, and proof size or prover time or something. And so like 0, 1 to the n so multilinear and univariate are two extremes of this trade-off curve. And, there are intermediate points, which most people have not really explored that carefully. But every so often you'll see a paper that looks at something like this. You'll see a paper that uses, like 0, 1 up to square root n to the 2 or something. People will talk about like, quote, bivariate sum check. And this is basically what they'd be using. So, every so often you will see a paper that is not at either extreme, but rather somewhere in the middle. Great. Other questions? Yeah. All right. Actually, before we talk about Lagrange interpolation, maybe it's useful to do some examples of multilinear extensions real fast. So we actually just saw some when I did the arithmetization tangent. So if you look at like the end function, let's say on 2 bits. So so this maps like 0, 0 to 0, like, so 0, 0, 0, 1 and 1, 0 all get mapped to 0, and 1, 1 gets mapped to 1. The multilinear extension of that is just x1 times x2. Right, like you can just check, like it's a multilinear polynomial, and it has this behavior on the Boolean hypercube. So that's maybe the simplest example. And similarly, we saw that OR twiddle of x1, x2 is x1 plus x2 minus x1 times x2. Not of x1, so this maps like, 0 to 1 and 1 to 0 is just 1 minus x1. And now we get to, let's do a more interesting one. Let's talk about the equality function. So let's say this takes as input two n-bit inputs, and outputs, 1 if, xi equals yi for all I, for I equals 1 to n, and 0 otherwise. Okay, so the multilinear extension of the equality function, let me just call this x and y, is the product from I equals 1 to n of xi times yi plus 1 minus xi times 1 minus yi. Okay, and how do you confirm that? Well, first note that the right-hand side is multilinear, right? Because each factor is multilinear, right? Like if you just fix I, xi times yi plus 1 minus xi times 1 minus yi has degree at most 1 in both xi and yi. And moreover, this is just testing. This is just equality, applied just to xi and yi. So you know, this maps, you can just check, it maps 0, 0 to 1, right? Because, you know, xi times yi is 0 at 0, 0, but 1 minus xi times 1 minus yi is 1 at 0, 0. So this handles mapping, you know, 0, 0 to 1, and this handles mapping 1, 1 to 1. Okay, but if, you know, xi equals 0 and y equals 1, or vice versa, then both of these terms are 0. Okay, and then all this is doing is producting together, you know, the sort of bit by bit equality checks. So, you know, this is sort of, you know, in logically speaking, in your head, you should think of this as end, but you're applying end, you know, to, you know, the, you know, equality of x1, y1 up to equality of xn, yn. Yeah. So in summary, like whenever I give a, you know, a polynomial and I say this polynomial is the multilinear extension of this function defined over the hypercube, the way to check that the claim is true is to confirm that the polynomial is, so you first you check one, the polynomial is multilinear. And two, the polynomial, if it's p, the polynomial p agrees with the function over the Boolean hypercube, which is the domain that the function we're trying to take the NLE of is defined. You know, so this is the domain of f. So we're gonna wind up doing this, like, you know, probably hundreds of times in this study group, where, you know, I'll write some expression, you know, some polynomial, and I'll say this is the multilinear extension of, you know, this function defined over the hypercube. And, you know, how are we going to confirm it? We're going to confirm that the polynomial I just wrote down is multilinear and that it spits out the right thing at any Boolean input. Okay. So I think these are the three most illustrative examples. Let me think if I want to do one more. Oh, I am gonna do one more. Let me pause here, see if anyone wants to ask a question. I'll do one final example if there aren't any.
I think we have one question. Okay. Suvi, do you want to just hop up on stage and ask a question if it's about this? Suvi, you should be able to speak.
Yes. Hello, Professor. So the loading extension of the circuit G, as was referred to the earlier notation, is what folks in the community do, is what was said. And it was said that multilinear extension is something that cannot solve, that we generally do not do. Then is the motivation for still going for multilinear extension is to make the number of interpolating sets smaller? Is that the general motivation?
It's a great question. So multilinear extensions turn out to be so nice in SNARK design because they have really nice properties that make them good for the prover. So when you apply sumcheck, the sumcheck protocol to, we never apply it to a multilinear thing for reasons related to the fact that, you know, the verifier cannot evaluate a multilinear thing quickly in many contexts. But often, so we apply it to like a degree 2 thing, often a degree 2 polynomial, not a multilinear one. But that degree 2 polynomial is typically a product of two multilinear ones. The fact that it's a product of two multilinear ones is key to making the sumcheck prover run really, really fast. Okay, and the structural property that is that enables that, it comes from what I'm going to discuss shortly, which is Lagrange interpolation. Lagrange interpolation is sort of a really nice expression for these multilinear extensions that ensures that the sumcheck prover is able to kind of exploit that expression to great effect to ensure that it can, you know, compute the messages really quickly. So I can try to say a little bit more than that. But one thing I'll mention right now, so this equality function, this is, as well as, you know, ends and ors and knots are also, you know, nice. So this is like really special. Okay, so what's going on here is, EQ, the equality function, has a domain of size 2 to the n, right? Its domain is 0, 1 to the, or sorry, I guess it's 2 to the 2n. Its domain is 0, 1 to the n by 0, 1 to the n, right? So the n as fairly big, I don't know, 20 or something. Its domain size is 2 to the 40, really big domain. But EQ twiddle, if I just want to evaluate it at like 1 point, can be evaluated in time order n, which is logarithmic in the domain, right? Like this expression for EQ twiddle lets you evaluate it, with, what is this, 2n multiplications and n additions or something like that. So it's really special, it's special because, like a snark verifier or anyone really can evaluate, its MLE can be evaluated, in time, way, way smaller, like logarithmic in the domain size. Okay. When we get to snark design, we'll wind up with a situation where some polynomials will arise where there's no way to evaluate and some MLE in time that's in the domain size. And we'll be forcing the prover to do that hard work, and ultimately trying to get the verifier to run, to only do things like evaluating EQ twiddle or something. So this will all make much more sense within the next couple weeks. But right now it's hard to say much more than that. But the one sentence answer to your question is MLEs turn out to be super, super important in snark design, mainly because they have some really nice structure that that the prover can heavily exploit.
Yes. So I'm trying to understand. This logic of logarithming in the domain size, the correct way to translate that is bringing down the number of interpolating set smaller.
No, I don't think so. All right, let's come back to this G. So the domain size, for the circuit is 2 to the n, right? If it's if it's a circuit, over n variables, right? You can feed into it like any true false assignment to those n variables. They're 2 to the n true false assignments, right? Okay. Now this particular polynomial, which extends the function computed by the circuit, this polynomial can be evaluated at any desired point in time, about like order circuit size, just by going kind of gate by gate through the circuit. So this G can be evaluated in time logarithmic in the domain size. Okay. But it's not multilinear. Okay. So what's going on is, like, if we only cared about verifier time, we actually could happily use this G in a protocol. And that's exactly what the IP equals P space result does. Right, because we're happy with the verifier, like evaluating G at a single random point and having the verifier run in this time bound. If as far as IP equals P space is concerned, where we're fine with like a polynomial time verifier, order circuit size is fine. The reason one reason we're really, really unhappy using this G in snark design is that the prover runs in time linear in the domain size, which in this case is, like bigger than we would like. We don't like provers that take exponential time 2 to the n. So what snarks will do is they'll often reduce the domain size of interest. People talk about like snarks as like a scaling down of the old like IP equals P space stuff. They'll say scaling. And kind of what they mean is in a snark, the relevant domain size, rather than becoming like 2 to the number of variables, it becomes just like basic number of variables or circuit size. So and then you want the verifier time to be logarithmic of that. So yeah, everything becomes clear with examples of protocols, but till we see the protocols, like, it's very hard to make anything concrete. So I would say, like, generally we want the verifier of snarks to only have to evaluate polynomials that it can evaluate very quickly, and very quickly typically means like logarithmic in the size of the circuit the prover is making a statement about. Okay, so to accomplish that, it means like we really want the domain size of the functions we're dealing with to be circuit size, and then we want the verifier to be able to evaluate those polynomials in time logarithmic in their domain size. And if we also want a fast prover, we're going to, the prover is going to have to run in time linear in the domain size. And so everything, that means we want the domain size to be circuit size and the verifier to evaluate, anything in time logarithmic in that. And so this is why, like, research on snarks and interactive proofs, like, didn't just stop at IP equals P space, because the domain size in IP equals P space that everyone was dealing with was too big. You needed to kind of scale everything down. And if you want to scale everything down properly, you really want degree, the polynomials that arise to have degree at most 2 in each variable or something like that. That's probably the most color I can give at this point. But anyway, specifically multilinear extensions rather than higher degree extensions, they are the nicest, mainly because they let the sum-check prover do a lot of really nice algorithmic things to run fast. And that, again, we're going to get to that in the next couple of weeks, but it's just very hard to say more than that right now. Okay. Other questions? Okay. Yeah, so this property that, like, this equality function has is pretty rare. This property that you can evaluate its multilinear extension in time logarithmic in the domain size, that doesn't come up like all that much, but it does come up. And that, when it does come up, it's a very powerful thing. So let me just do one more example. Okay, let's say we have a matrix, but the matrix is like block diagonal. So this actually comes up in ZKVMs all the time. Jolt, for example, this is like absolutely central to Jolt. So let's say we have this really big matrix. Let's call the big matrix B, but B just consists of a bunch of copies of a very small matrix A. So let's say B is 2 to the K copies of A, where A is, let's say, I don't know, 2 to the L by 2 to the L. Okay, and so I don't know, say A is 64 by 64, that would mean L is 2, 4, 8, 16, 30, 2 to the 6, I think L is 6. But K, maybe K is 30, so 2 to the 30 versus a 64 copies of a 64 by 64 matrix or something. Okay, so let us index rows and columns of B, but like we're going to view A and B. Sorry. Let's say let's view A as a function whose domain is 0, 1 to the L by 0, 1 to the L. Okay, and this perspective is really important. So it's often the case in snark design that I give you a matrix or a vector, and I want to take the multilinear extension of that matrix or that vector. Okay, but what does that even mean, right? Like, in order to define a multilinear extension, I need to have a function whose domain is the Boolean hypercube. right? So how can I view like a matrix or a function, a matrix or a vector as a function over the hypercube? Well, all I do is interpret, the entries of the hypercube as indices into the vector, right? So if I have an I and a j in 0, 1 to the L, I'm going to interpret this as, the binary representation, of a row of A. And this was the binary representation of a column of A. And I'm going to overload notation here. So I'm going to define Aij, here, I and J are in 0, 1 to the L, as the ijth entry of A, where here they're like, row and column. Right. So just as an example, let's set L equals, like, let's say A is, just 2 by 2, 3, 4, 5, 7. Like, let's say that's A. The way I'm interpreting this matrix as a function over the hypercube is, A of 0, 0 is 3, A of 0, 1 is 4, A of 1, 0 is 5, and A of 1, 1 is 7. Okay. So I want to view, the matrix A as a function on the hypercube, and that way I can talk about the multilinear extension of A. So A twiddle is the unique multilinear extension of this function. Okay. All right. So here, here's the key claim. So I can now, I can index row, if A is, has 2 to the L rows, and B consists of 2 to the K copies of A, right? Then I can index rows of B, as like a row of A, like specifying a row of A, followed by like a copy of A. And similarly, I can index columns of B by, which copy are you in, which copy of A are you in, and then which column within A are you in. Yeah. So if B has this block diagonal structure where it just has 2 to the K copies of A along the diagonal, and the rest is 0. Okay, then B twiddle of let's say X row, comma, how do I want to say this? X copy, Y row, Y copy can be expressed as A twiddle of, so we call it row A and row A. So it's A twiddle. So you feed the row A stuff into A times EQ of X copy, Y copy. Okay. So what's going on here? Like, how do we verify that this fact is true? All right. So remember, whenever I make a claim like this, what you have to confirm is that the right-hand side is multilinear. So we have to check that the right-hand side is multilinear. And secondly, check that the right-hand side, takes the right values, on Boolean inputs. So over, X row A, X copy, Y row A, Y copy in, what's it, 0, 1 to the L by 0, 1 to the K by 0, 1 to the L by 0, 1 to the K. It takes L bits to tell you a row of A, K bits to tell you what copy you're in, L bits to tell you a column of A, K bits to tell you what copy you're in. Okay, so the right-hand side is clearly multilinear because A total is multilinear and EQ total are multilinear, and we're feeding like disjoint variables into the two, right? So, you know, this thing has degree 1 in each of the variables we're feeding into it. This thing also has degree 1 in each of the variables we're feeding into it. We're multiplying them together, but they're over disjoint variables, and so the whole thing still has degree 1 in each variable. So the right-hand side is multilinear. And then to check that the right-hand side, you know, agrees with the left-hand side at Boolean inputs, like all this is saying is that, you know, like if you're not in the same copy, if you're dealing with like a row and a column that don't capture the same copy, you're in one of the all zeros components here. You know, like if I look at, you know, this row and this column, you know, if you know this row is copy, you know, 3, but column, you know, so the row copy is 3, right? We're in you know, copy 1, copy 2, we're in copy 3 down here. Well, it's 4, copy 4. We're in this copy for the row, but we're in, you know, the second copy for the column. And so, you know, you're in all zeros land. So this is saying like, hey, if your row and column are not in the same copy, the entry is 0. You know, so EQ twiddle will spit out 0 when you feed in the copy variables if they're not the same copy. But if they are in the same copy, EQ twiddle spits out 1, and then you just, you know, you spit out the correct entry of A. Right. So coming back to the picture, right, if I want to know like this entry of B right here, well, you know, the row variables for this dot is, let's say this is, I don't know, you know, this would be copy 2 of A, and the row would be 1 and the column is 0. So the row is 1 and the copy is, you know, 1, 0. You know, this is saying copy 2. And this is saying row 1 in binary. And the column for this dot would be, what is it? Again, copy 2, you know, which is 1, 0 in binary, and column 1. So, you know, so column 1 of copy 2. Yeah. And so you get this nice expression. So B is like a huge matrix. But of course, you know, it's not much is happening in B. You know, B has billions of entries because there's billions of copies of A in it. But like, you know, everything is 0 except for the, you know, if you're, you know, along the diagonal. And so that's what this MLE expression is capturing. You know, it's saying, hey, like, B twiddle is all zeros unless you're in the same copy of A. If you are in the same copy of A, you know, the row is in the, you know, the row and column, you know, match up in terms of what copy of A they're referencing, then we're just dealing with A here. Okay, and so this is a super important fact that comes up over and over again in snarks for, you know, what I call uniform computation. So that means any ZKVM, you know, any time you're doing the same computation over and over again, any data parallel thing, you know, you when you're doing the same thing over and over again, the same simple thing over and over and over again, right? If you do it for a billion times, you wind up with like a billion copies of the same little thing. And, you know, that this is the kind of matrix that arises in such snarks. And so the fact that a verifier can actually run in time, you know, proportional to the small thing, right? And the big thing, you know, kind of gets captured just by this equality function, which can be evaluated very quickly in time logarithmic in the number of copies, is really, really important. So that is the last example. If it didn't make a ton of sense to you, hopefully you got the gestalt, the gist, and it helps to see this sort of thing multiple times. Okay, let me pause there, see if anyone wants to ask any questions. Questions? Can someone confirm there are no questions?
try. There are a couple. I'm gonna pull them onto the stage.
Hi, can you hear me?
Yep.
Hi, yeah, sorry. So I was gonna ask, so first of all, I'm a noob here, and
Mhm.
sorry, the question is too silly, but since you brought up like ZKVM here, just on like high level, to clarify my understanding, is so circuits compared to like something like ZKVM, like RISC-0, where there are no circuits, and if I am writing circuits, then like how do they compare with like execution trace, and then like you know how on RISC-0 you have like state transitions, and then like they are like recursively added and then created like with a start um, proof. Then how do circuits compare here? And especially when you said when you do some like simple stuff over and over and over again, which like approach here is more efficient?
Yeah, great question. There's a lot to unpack there, and so it's always dangerous to ask me a question like that. And I always say I'm going to try, my best to keep it short and fail. But so let me try. So the distinction here in about whether or not this kind of repeated structures, block diagonal matrices comes up, it arises in the context of both circuits and ZKVMs. In fact, I would not say there is no circuit in RISC-0. It's just the circuit that's there. It's really like a constraint system, which is a slight generalization of a circuit. Kind of captures the execution of a VM. Okay, but a VM by definition does the same simple thing over and over and over again. So roughly a VM just what does it do? It runs fetch, decode, execute over and over and over again. Every cycle of the CPU of the VM, like that's what you read the program counter, you figure out like what that means in terms of which primitive instruction should be executed next, and then you execute the instruction. And, this is a little simplification. There's like a memory and stuff too, but basically it's just doing fetch, decode, execute, fetch, decode, execute, fetch, decode, execute. And so all the ZKVMs really do have circuits somewhere, but circuits in some kind of loose general sense as we move beyond like literal like ends and OR gates or something like that. And then if you actually look at what those circuits are, it's like the same little circuit that just does like little circuit would be fetch, decode, execute, like capturing one cycle of the VM, and then we would there'd be one copy of the circuit for every cycle. So if you run the RISC, like a RISC-V program for 1 billion cycles, which people today consider to be a lot of cycles, but is really, in the scheme of things, like very little, like your laptop would run that in under a second, you'd have 2 to 30 copies of like the fetch, decode, execute circuit. And so what I would say is, the VM abstraction actually guarantees that the circuit you care about has exactly the structure, that it's the same little thing repeated many, many, many times. And so that's exactly why this sort of situation is so important. It lets the verifier time sort of be mostly independent of the number of copies, that is the number of cycles the VM ran for, and really just proportional to like the complexity of one cycle of the VM. RISC-V is like a pretty simple VM in the scheme of things, and so the circuit capturing one cycle of it doesn't have to be all that complicated. In fact, in Jolt, this quote circuit involves just like 40 constraints and like 80 variables or something. Now, Jolt is doing a lot of work outside of the traditional constraints, and it pushes it into lookups. So this sounds a little more impressive than it is. But yeah, so there's, to wrap this up. Hopefully, everything's been relatively coherent so far. Your question is a really, really important one, and one that I think there's a lot of confusion about still. There's this issue where some constraints or circuits, some circuits are uniform, which roughly means they kind of do the same simple thing over and over. and some are non-uniform, meaning, they do not do the same simple thing over and over. Okay, and different snarks are targeted at different settings here. And so I'm going to just spend 1 minute on this because I think it's really important. But so things like Planck, Marlin, Growth 16, they were basically designed for the non-uniform case. So they can handle like any circuit, and which is good. On the other hand, their costs like do not really get better unless you like modify them in certain ways. If the circuit is uniform, so if the circuit has repeated structure. Okay. Starks are targeted at something called air, or so any snark for air mainly. Air is a kind of circuit, a kind of constraint system, which has uniformity baked into the definition. So they only apply to uniform. If you want a fast verifier anyway, like, there are some small caveats to this, but like high level, the point holds. And then most sum check based snarks, like Spartan, or for example, they sort of, have like two modes, one for uniform and one for non-uniform. And basically, and you can also sort of be in between the two, but we don't have to get into that. And so in the uniform case, that means you can get major cost savings compared to the non-uniform case. But, but you're still able to handle non-uniform circuits if that's what you're handed. Okay, and so, I think to a reasonably large extent, the view that like Starks are sort of faster than like, Planck and Growth 16, a lot of that is really just coming from them leveraging uniformity in a way that Planck, Marlin, and Growth 16 were not really designed to leverage. Okay. It's a very multi-dimensional design space, snarks, right? So there's like, hashing commitment schemes versus elliptic curves and all sorts of other stuff. So, if you ever focus on like just one dimension of the design space, you're of course, hiding a lot of complexity and nuances. But roughly speak, like this uniform versus non-uniform dimension, people just generally seem a little bit confused about. And, most of the things we want to prove today have repeated structure. You're doing the same relatively simple thing over and over again. You're evaluating SHA many times because it's like many Merkle authentication paths or something. Or you have a ZKVM and you're applying fetch, execute, decode over and over and over again once per cycle of the VM. And so, any setting where you have that repeated structure, you really shouldn't use, at least if you care about prover time, like Planck, Marlin, or Growth 16 directly. They were not designed, it's not a dig at them. They just weren't designed to take advantage of that structure. And so, yeah, that's why a big part of why you see Starks and these sum check based snarks getting more and more popular. And I'm not sure how much people realize like that there's a lot of that going on, that like you're really they're leveraging uniformity, and these other ones weren't designed to do that. So it's your question is not really like a circuit versus VM issue. It's is there repeated structure or not issue. And the VM abstraction just intrinsically forces repeated structure into the computation. That's why, but that's a big part of why we see this repeated structure so much today.
There were a couple more questions. I've got two people who are invited to come up stage. So Nakul, if you can hear this and you want to hop up. And if not, Build. So Build's question was, Nakul, you should be invited. You should have the option to come on stage. Yeah, you have been invited. I think there is a button on your screen that says come on to stage. I can see on my end that you're invited. Okay, I'm gonna pass along Build's question first. So isn't an execution trace just a different representation of a circuit where every memory register change is basically a circuit gate or a constraint?
Yeah, great. So the execution trace is sort of, I would call it like the untrusted advice, or it becomes kind of part of the witness, if you will. And then what the circuit or constraints wind up doing is confirming that the execution trace is valid. So that like if the prover claims that the output of this primitive instruction on these two inputs is blah, that indeed that is correct. And so, yeah, I mean, like the circuits or constraint systems that implement ZKVMs, they tend to look like this. So, you have the prover like commits to an execution trace, what's claimed to be an execution trace for the VM, and the circuit kind of, so this is like everything that happened at cycle 1, this is everything that happened at cycle 2, and so forth. And then what the circuit will do is it just sort of, has a little checker, like check that, what happened at cycle 2, like follows correctly from cycle 1. Check in general that, cycle I, what the execution trace happens at cycle I, like is happened correctly, based on whatever the state of the machine was, after cycle I -1. So you have the same little check done over and over and over again, just on like adjacent entries of the execution trace. Sorry, so I should, these, so yeah, so the picture got gross because I'm bad at this, but like, so you just have like, a simple checker, one per cycle. And if you look, if you're dealing with like an actual constraint system, this literally becomes what the constraints look like. Like this is just checking cycle 1, this is checking cycle 2, this is checking cycle 3, and maybe there's a little bit of overlap because like cycles 1 and 2 get checked together, and 2 and 3 or something. So maybe the actual picture is like there's they half overlap in the a little bit or something, but close enough to just being block diagonal. Does that make sense? Yeah, so there's one little constraint system per cycle, and you just and you have a billion cycles, so you just apply the same checker a billion times, once per cycle.
Cool. We have another question which says, you mentioned that the MLE of EQ can be evaluated at a random input in time O of number of variables.
Mhm.
This is only true for simple functions like EQ and not for arbitrary MLEs, right?
Yes, absolutely. And in fact, like if I give you like a Boolean circuit, that we discussed before, on n-bit inputs, the ability to evaluate the MLE of the function computed by this circuit actually lets you solve the satisfiability problem for that circuit, which means we, very, very strongly think that, if I hand you a circuit, thereby specifying a function, whatever function the circuit computes, it should take exponential time to evaluate the MLE of that function at a randomly chosen point. So EQ is like very special. Yeah.
I think he might have a follow-up that he's typing, but for now so the question is, evaluating an arbitrary MLE in polynomial time implies NP in BPP. I don't know what much of that means.
Yes, essentially. So like if okay, so let's say, I'd make it a little more precise. So let's say the way I specify this F is by, F is specified, by giving, say, a size n Boolean formula computing F, size S Boolean formula computing F. Okay. If F twiddle can be evaluated, in poly S time, let's say order S, but whatever, poly S time, then NP equals BPP. Yeah. And in fact, the error is one-sided. So I actually think NP equals like RP or something. But basically it means like, you know, there just is no efficient algorithm to do this. Like you're gonna need time like 2 to the S, not poly S, unless NP equals RP, which it doesn't. Great. Yeah. So EQ is super duper special. All right. Okay, so since we're so far over, I do want to wrap up multilinear. I, you know, still haven't done the main topic today. Great questions as always. Yeah, so I want to. So multilinear Lagrange interpolation has the following goal. So the input to the algorithm is all 2 to the n evaluations of some f. You know, whose domain is 0, 1 to the n. So, you know, EQ is really special, right? Like, you know, we can evaluate EQ at any desired point in time order n, but in general, we just can't hope to do that. So the best we can actually hope to do well, I mean, if we're going to describe F in this way, you have to at least read all 2 to the n evaluations. So the goal, you know, let's say there's a second input, you know, R in field to the n, and the goal is to evaluate F twiddle of R in order 2 to the n time. Okay, and this is, you know, this looks big, and in general it is big, depending on what n is. But like in snark applications, you know, in snarks, you know, like n will be log of circuit size or something. Okay, and so if it's the prover who's doing an evaluation like this, like order 2 to the n time is okay. So order 2 to the n will be like order circuit size. All right, and like in general, for reasons we just discussed, like you can't, you know, if f is like a completely arbitrary function, you really can't hope to even specify it, you know, faster than 2 to the n time, much less evaluate f twiddle of R in 2 to the n time. So this is kind of the best you can hope for. Any questions? So multilinear Lagrange interpolation relies on the following facts, which, you know, in our rambling discussions today, we've actually sort of covered some background that is going to let me sort of shorten this presentation a little bit. So it wasn't a complete waste of time to have all of this discussion. So for any f, f, you know, whose domain is 0, 1 to the n, you know, and whose range is some field, f twiddle of x can be written as follows. So, well, let's say f twiddle of R. So sum over, let's say y in 0, 1 to the n of f of y times EQ twiddle of R comma y. Okay. So let's prove this. Again, whenever I make a claim like this, it's the same thing every time. Make sure the right-hand side is multilinear, and confirm that it has the right evaluations over, you know, Boolean inputs. So let's start with the right-hand side being multilinear. Well, this is just because this holds because EQ twiddle is multilinear, so it has degree 1 in each variable of y. F of y is like just a value, right? This is not, you know, if the input, you know, to the function is like, you know, it's a list of 2 to the n evaluations, I don't know, 3, 4, 5, 7, you know, for each y, you know, like, you know, y being 0, 0, f of y is just 3, you know, so, you know, this is just like a field element, you know, don't think of this as like a polynomial in y, it's just like a field element. And so this is just, the right-hand side is just a weighted sum of multilinear things, and, you know, a sum of multilinear things is multilinear. Okay. And I'll do an example in a second so you can see this. But Yeah, so the right-hand side is multilinear. So the other thing we have to check is that the right-hand side, takes the right, has the right input-output behavior, so it takes the right evaluations, whenever R is in 0, 1 to the n. And, what's happening here is, oh, question? No questions? Okay. So what's happening here is if R is in 0, 1 to the n, this equality function will just kill every, for every y that is not equal to R, this equality function will spit out 0, right? Remember, equality over Boolean inputs, of x, y, if they're both Boolean, is 0 unless x equals y. Okay, but if x equals y, so if R is Boolean, so R is like the x. If R is Boolean, when y equals R, EQ twiddle spits out 1. So that'll be the one term of the sum that is not killed by EQ twiddle, and there we have 1 times f of y, which again f of y for this one term y equals R. So you spit out f of R. Okay, so this is what the same sort of thing that happened in univariate Lagrange interpolation. The univariate Lagrange basis, kind of each basis polynomial picked out exactly one element of the interpolating set. Each equality polynomial here is, there's 1 per y. Each equality polynomial is picking out exactly one element of the interpolating set, and then spits out, for that one element you spit out 1, and then you multiply by the desired evaluation at that element. Okay, questions?
Hi, Professor. I had a quick question motivation for MLE as opposed to the higher degree circuits is prover time linear in the domain size, as was stated. So then I'm a little confused about how this repetitive substructure A view that was just presented, this observation, how does it formally help the prover as opposed to the higher degree circuit technique?
Yeah, so what's going to happen, these equality polynomials are super nice. So not only can they be evaluated, very quickly by anyone, verifier or prover, but they also have this really nice structure going way back up when I defined that, when I gave an expression for them here. So they operate 1 bit at a time, so, they check, does xi equal yi, and it's just a product of the results. Okay, so in sum check based snarks, in each round of sum check winds up kind of fixing another variable I to a random value. Okay, and for higher degree extensions, like so you often have the situation where, how do I want to say this? Like you might have a function, let's say that's evaluates to 0 almost everywhere. Like it would call it sparse or something. There's only very few inputs where it doesn't evaluate to 0. But that when you look at it only over Boolean inputs, right? So it evaluates to 0 at almost all Boolean inputs. But if you evaluate it at a random input in the whole field, it tends to be non-zero, right? Okay, and then so in the sum check protocol, each round another variable gets fixed to a random field element. Okay, so in general, in non-multilinear, when you're dealing with non-multilinear things, as soon as you fix even one variable to a random field element, you might totally lose the sparsity, right? So maybe I need a picture here. So say this is 0, 1 to the n. And say, f is mostly zeros, and, it's just got a handful of points where it's non-zero everywhere. So these 3 dots, it evaluates something non-zero, and everywhere else it's 0. So in general, if I look at like a non-multilinear extension of f, it might be the case that if I feed in, a random field element for the first variable, and then, so x prime, let's say, is in 0, 1 to the n minus 1, but R1 is in the whole field. It might be that you wind up with, so the domain of this G, ranging over all x prime is half the size of this original domain. So it could be, so now we have G's domain 0, 1 to the n minus 1. And it could be that this whole, G is defined over the whole field, but we're only paying attention to 0, 1. So it could be this whole, over the whole hypercube, G is non-zero. Okay, but the multilinear thing often still has the property that it's very sparse. And the reason is basically this winds up happening because EQ twiddle has this variable by variable structure, so that if I this will all become much clearer in the coming weeks, but it goes one variable at a time. And the point is, like, only one factor in this product needs to be zero to make the whole product zero. Okay, so it could be, so if I fix one variable to be outside of the hypercube, I might cause, the first term in this product to become some crazy field element. But all of the other terms in the products have basically been unaffected. And so the sparsity kind of remains. You still keep the sparsity because you wind up, even after round one, you still, are only caring about inputs to the remaining variables that are Boolean. So that's the sort of thing that makes multilinear polynomials so good for SNARK design. This sort of variable by variable structure in them means, like, even as you start replacing some variables with random field elements, so that now you have to worry about how polynomials behave when those variables are not in 0, 1 anymore. You still maintain the structure coming from the remaining variables that kind of are still we only care about Boolean values for the remaining variables. So that's what's happening. That's why multilinear things really matter in SNARK design. It's very hard to see this the details until we just see the protocols. Was that a little bit helpful?
So the prover staying linear in the domain size has something to do with the sparsity of the matrix and not. So I'm a little bit. Yeah.
So in some contexts, yes. In other contexts, I'm trying to think. Yeah, okay. So in some contexts, absolutely. In some contexts, you're dealing with with sparsity, and this is exactly what's going on. In other contexts, if you use non-multilinear things, you could still get a prover that's like quasi-linear time, but it's so like sum check proceeds in, if you want to do a sum over 0, 1 to the n of some n-varied polynomial, that's what sum check does. We haven't seen sum check yet, but we will soon. Sum check has n rounds. Okay, and if for any G, not just multilinear ones, the prover, in sum check, at worst, needs to evaluate G at 2 to the n points in each round. Okay, so and in fact, it's actually the number of points that we sum over halves in each round. So it's 2 to the n minus I points in round I. But whatever. Let's just say 2 to the n in each round. Okay, so you don't need multilinear to get so P can always run in time, like order 2 to the n times time to evaluate G at one point. Okay, and often even with non-multilinear extensions, like this is like order 2 to the n times n or something, depends. But so with non-multilinear extensions, you can get this sort of time bound, which is like not bad. Like if 2 to the n is circuit size, is like the size of the circuit you're dealing with, like this is called quasi-linear. This would be like order circuit size times log circuit size. Like that's not bad. Okay. But it's we can do better. And with multilinear things, you can, if G is kind of built as a product of a handful of multilinear things, you can actually, so with MLEs, you can actually get prover time of order 2 to the n, which is, this is like the best you can hope for in general, because like just computing the right answer in general is, might be 2 to the n time. The sum is over 2 to the n terms, just evaluate if there's one term per gate in the circuit, just evaluating the gates in the circuit gate by gate takes 2 to the n time. And so, yeah, I mean, the benefits of MLEs, it depends, like in settings where G is really sparse, meaning over the hypercube, it evaluates to 0 at almost all points, the benefits of MLEs is enormous. Okay, in settings where G is not sparse, the benefits of MLEs are smaller, but still like really, really do matter. They might be like 1 log factor or 2 log factors or something like that. Is that a little helpful?
Yes, sir. Certainly is. Thank you.
Great. So a very prescient question. And again, the more prescient the question, the harder it is to answer before we start seeing some of these protocols, the details of them. Okay, more questions? Right. So yeah. So as far as the verifier goes, again, we're generally not going to be happy. It depends, in context. But in many cases, we don't want the verifier to run in time linear in the domain size. So we don't want the verifier to evaluate the sum on its own. But we will be totally fine with the prover evaluating this kind of sum on its own. And so the sum, well, it can be useful both for the prover and the verifier. This expression, but it's especially useful for the prover. Since we typically will be happy with the prover running in, time linear in the domain size, which is 2 to the n here. That domain size is often circuit size. So n would be log circuit size, 2 to the n is circuit size. Okay, so this is just a fact. And then, so multilinear Lagrange interpolation, multilinear Lagrange interpolation. That term could just, sometimes it just refers literally to this expression. Okay. But I sort of framed it as an algorithm. So it's like a fast algorithm, that, given as input, the f of y for y over 0, 1 to the n, for all y and 0, 1 to the n. So that is given every coefficient in the sum, quickly computes the sum. So quickly computes, sum over y and 0, 1 to the n of f of y times eq twiddle of r comma y. Okay, and because eq twiddle can be evaluated at any point in order n time, like trivially, like the trivial algorithm, will just independently evaluate eq twiddle. So evaluates eq twiddle of ry, kind of in order n time per y. Okay, and so that runs in order n log n, 2 to the n times n time. Which is, if the input size to this algorithm is 2 to the n. So if I call, the input size, so if input size is, if I denote it, by n, capital N, which is 2 to little n, this is, the same as order n, capital N log capital N. So that's the best you can hope for up to the log factor. And the algorithm, the downside is the log factor, which actually does matter in practice. Like that log factor can easily be like 20 or 30 or something in practice. The benefit is the algorithm actually doesn't care what order the f of y's are presented in, and can kind of process each f of y as soon as it sees it, and then it no longer cares what f of y is because it sort of handled the y term of the sum and it's just free to move on. So this algorithm has a nice property that we call streaming, but don't worry about it. And then so there are algorithms that run in time, that actually do run in linear time. linear in the size of the input here, which is capital N, with 2 to the little n. So that run in order capital N time. And the most popular one, what it does is it, so one way to do this. So it's due to a paper of Vu and others called Allspice from like 2013. But it's a very simple observation, and it is that you don't have to evaluate, all the EQ twiddle polynomials independently, right? So maybe I won't go through the details now because we're over time, but like there is a way to compute, EQ twiddle of R comma, all zeros. Well, up to EQ twiddle of R comma all ones, so that is, all 2 to the n, vectors here, in the right hand, in the second half, in 0, 1 to the n. There's a way to get all of these evaluations in order n time, and once you have them, then you're done basically, because then this sum is just like an inner product between the evaluations of f and the evaluations of the EQ twiddle, as y ranges over 0, 0, 1 to the n. So evals of EQ twiddle of R comma y. So then you just go over, you iterate over all y and you multiply f of y, which, was handed to the algorithm as part of the input, by the relevant evaluation of EQ twiddle that you already computed. And maybe I won't skip the details, but this is like the end of section 4, I think, of the, end of chapter 3 of the book. It's that achieves this. And if you're very interested, there's a new algorithm of Ron Rothblum, which achieves the same runtime. And it looks more like the univariate Lagrange interpolation algorithm that we saw a couple weeks ago. So there, if you express the univariate polynomial p of x as some, in the Lagrange basis, the univariate Lagrange basis of p of I times the ith univariate Lagrange basis polynomial. What we did was we said, hey, like, you can compute, like lambda delta 0 of R in order n time. And then we said, like, given delta 0 of R, you can compute delta 1 of R in roughly constant time. There was like some nuisance about inverting something not being constant time, but don't worry about it. And then, in general, given delta I of R, you can compute delta I plus 1 of R in constant time. So you sort of spend linear work just to get the first Lagrange basis polynomial in the univariate setting evaluated at R, but then you spend an about equal amount of work across all of the remaining evaluations. And so Ron's algorithm does something similar, I think, for multilinear Lagrange interpolation, where you sort of go over each term of the sum. I don't think there's that sort of linear cost just to get the first term for Ron, but you go over each term of the sum, and like, given the current the evaluation of EQ twiddle for the current term in constant time, you can get the evaluation of EQ twiddle for the next term. And in that way, you go like, one term after the next, spending constant time to, figure out what the next term's EQ twiddle evaluation is. And so the last thing I'll say today is the multilinear Lagrange basis. So that is the polynomials, like, okay, so I call it like chi y of R So this is the y like multilinear Lagrange basis polynomial. Okay, and this is just EQ twiddle of y comma r. Okay, and so what's happening here is another way of writing this is, the product from I equals 1 to n of yi times ri plus 1 minus yi times 1 minus ri. And remember here, r can be anything in the whole field, right? It's just, some evaluation point for this polynomial, but y is in 0, 1 to the n. There's one Lagrange basis polynomial for every point y in 0, 1 to the n, which means another way of writing this sum is like, so if y is 0, sorry, if yi is 0, then we get a 1 minus xi or 1 minus ri. And if yi is 1, we get an ri. And so let me do a quick example for n equals 2. So like the 0,0th Lagrange basis polynomial would just be 1 minus, so r1 comma r2, since it's two variables here, would just be 1 minus r1 times 1 minus r2. The 1/0th Lagrange basis polynomial would be r1 times 1 minus r2. The 0/1th would be 1 minus r1 times r2, and the 1/1th would be r1 times r2. Okay, and then just as one more example with a picture, so let's say again n is 2, and let's say we have the evaluations of f are 3, 5, 4, 7, then f twiddle, let me switch from r to x, would be the following. So it'd be 3 times 1 minus x, let's call this x1, x2, 1 minus x1 times 1 minus x2, plus 5 times, so what is this, 0, 1, 1 minus x1 times x2, plus 4 times, so 1, 0, the Lagrange basis polynomial for that is x2 times 1 minus x1, plus 7 times x1 times x2. Anyway, yeah, so, you get 3 times the 0,0th Lagrange basis polynomial, 5 times the 0,1th Lagrange basis polynomial, 4 times the 1/0th Lagrange basis polynomial, and 7 times the 1/1th Lagrange basis polynomial. That is multilinear Lagrange interpolation. Yeah, so hopefully that was followable, even though I covered it pretty quickly. And again, so just as with the univariate case, the fact is, you can kind of just take this as fact and not worry about the details. But if I give you all 2 to the little n evaluations of a function over the hypercube, as well as the desired evaluation point, in time linear in the number of such evaluations, you can evaluate the multilinear extension at the desired evaluation point. And it's sort of just, if you wanted quasi-linear time, you would just kind of very naively apply the Lagrange interpolation expression. But if you're a little smart about things, you do not need to spend logarithmic time per equality evaluation, per Lagrange basis polynomial evaluation. You can kind of get all 2 to the n Lagrange basis evaluations at the relevant point in order 2 to the n time. Okay, so that's everything I wanted to cover today. But if you have any questions about that, please do ask. Questions?
I'm not seeing any questions in the chat. And I have one request to speak. I'll let him up. Skanov, if you would like to speak, you can. There you go.
No, I kind of requested long time in the middle of the thing, and it was contextual. So, not now. Thank you.
Great. So in that case, we can wrap up. We are at 2 hours, so we should do that, I guess, regardless. So that's multilinear polynomials and Lagrange interpolation. So we're ready to talk about the sum check protocol, which I'm psyched about. So we'll do that next week. So have a great weekend. What is it, the middle of the week? Well, have a great week, and we'll talk about sum check next time. I look forward to it. Talk to you all soon.